Salutations, mini mathematicians. I hope you're having a wonderful week and you're ready to get into Module 7, functions. Functions have the word fun in them. So let's get into 7.1b lesson, which is function rules and function notation. And if you're still keeping up a notebook, I want to go over the purpose with you. If you need more time to write it down, you can always pause and write it down. But for everyone, it's really important to know what our goals are for this lesson. So our goals for this lesson are to define function notation, f of x. We can also use g of x, r of x, but f of x is a synonym. Synonym means words that mean the same thing, like pretty, beautiful, up, above, like things like that. Synonym, the same. So f of x, it's a synonym, means the same thing as y, or output, or range, and it's read as a function of x. So f of x, f as a function of x. We're going to practice evaluating using function notation and writing a rule or an equation in function notation given a table. And then given a table or mapping, we're going to determine if that relationship is a function or not. So again, f of x is an output and x is an input. So let's get started on our lesson. 7.1b lesson, function rules and function notation. So there's a little bit of reading we will have to do here. Another way to think about the x and y variables is as input and output values. Input is the x and output is the y. So a lot of times when I see a word that means x, I'll put x on top of it. If I see a word that means y, I'll put a y on top of it just so my brain can make those connections. To better understand how input, x, and output, y, values, are related to a function, we'll investigate the following vending machine analogy. Vending machine snacks. When you buy snacks from a vending machine, you push a button, input, and out comes your candy, output. Let's pretend that G4 corresponds to a Snickers bar. If you input G4, you would expect to get a Snickers bar as your output. If you enter G4 and sometimes the machine spits out a Snickers, and other times it spits out a Kit Kat bar, you would say the machine is not functioning. One input, G4, corresponds to two different outputs, Snickers and a Kit Kat. This situation is represented by this mapping. So this mapping is not a function. And remember today we really want to think about, is the mapping a function or not? So taking a look here, the input G4 corresponds to a Snickers or a Kit Kat. Given my input, I cannot determine the exact output I will get. So this is not a function. If it was a function, one input would correspond to exactly one output, just one snack. I would know what snack I'm getting. So what would a mapping look like for a vending machine that is functioning properly? So a mapping has two ovals. The input is always on the left and the output is on the right. And so if I had an input of G4, it would correspond just to one snack, like just a Snickers. And maybe you had a different input, like a G6, and that corresponded to a Kit Kat. So we have each input corresponds to exactly one output, meaning, yes, this is a function. The machine is functioning properly. So let's take a look. The next paragraph. When the vending machine is functioning properly, each input corresponds to exactly one output. Each X corresponds to one Y. The snack that comes out of the machine is dependent on the button you push. If you want a Snickers, you have to push G4. We call this variable the dependent variable. So output, or Y, or dependent. Input is X, or independent. The button you push is called the independent variable. With some vending machines, companies may stock super popular items in multiple locations in the machine. This can be represented by the mapping to the right. Does this mapping represent a function? Why or why not? So because the vending machine guy can only come and stock it, once a week, or maybe it's twice a month, depending on our candy needs for that machine, Twix is the most popular candy in this machine. So they decided to fill 3 different rows with just Twix bars. So you could press E3 and you'd get a Twix. You press A4, you'd get a Twix. What if you press D6? You know you're getting a Twix. So does each input correspond with exactly one output? Yes, E3 only corresponds with one output. A4 corresponds only with Twix. D6 corresponds only with Twix. So yes. And in this way we can say, another word for X. Do you guys remember another word for an input or independent? Another word is domain. That's another synonym. And then the Y value is called the range. Perfect. Ooh, that E is a little messy. Okay. Does this mapping represent a function? Yes. Each input has a unique output. I know you might say, hey, that word unique, but all of them go to Twix. That's okay because it's unique to that input. It's unique to that input. So we can say it's unique because it has one and only one. Each input has one and only one output. But that output could belong to different inputs. For example, I have 4 siblings. Mrs. Barr, really? Yes, I do. I have 4 siblings. So there's 5 kids in my family. All 5 of us kids have one dad. So each kid has a unique dad because it's just one dad. Each child only has one and only one dad. So you can think about it that way too. So let's take a look at what the next part tells us about. We're going to get into that range and domain words. Okay, in a function, the set of input values, X, is defined as the domain. The set of output values, Y, is defined as the range. So more words that mean the same word. When the specific input or X value is inserted into the function or rule, the output of the function of X, f of X, the output is a function of X, which we call f of X. The output is represented as f of X, which means the function evaluated at X. Remember what evaluated means. Evaluated means we substitute into an expression and simplify. So that's exactly what it means. F of X, whatever that X value is, we're plugging in, we're substituting into that equation or expression and simplifying. The output is represented as f of X, which means the function evaluated at X, and is read f of X. This is called function notation. Imagine the input value going into a function machine and coming out a different number, the output value. So it goes in as X and it comes out as Y. Something is happening to that number inside the function machine. So you get your input value, your domain, we can also call it X or independent variable. Goes into your function rule, boop, bop, beep, bop. Maybe it's getting added, maybe it's getting multiplied, maybe it's getting divided, maybe it's being raised to an exponent, and then it pops out after it gets evaluated as your output value, your range, your Y value, your dependent value, or your f of X. So Y has one extra synonym for it. And here's another way we can look at it. X value goes into your function rule, boop, bop, beep, bop. Maybe it's being subtracted by 1,000, and then multiplied by 100, and then divided by 5. And out comes your f of X, your output value. Cool, let's keep going. Number 1, it says examine the table of values to complete, oops, you can't see that. Examine the table values to complete the following. What values represent the domain? So when we give values of the domain, we're going to give them in set notation. So set notation, we use curly brackets. We can use X and a colon. And these curly brackets, we're going to list them from least to greatest. And we don't repeat any values. Even if they're repeated here, I wouldn't repeat any values. So the smallest X value, remember our domain here, is -5, then -3. We separate them with commas. 1, 3, and 5. And we close it with another curly bracket. And that's our set notation. And you're going to be using that a lot next year too, set notation. What values represent the range? Well, here we're asking, do you understand that range means your Y values? So here's your Y values, and it's also your output, your f of x. And your Y values here, again, set notation, we're going to use curly brackets. We're going to list them from least to greatest. 15, 17, 21, 23, and 25. And again, using set notation, if we had a number repeating, we wouldn't list it twice in set notation. We just list it one time. Okay, what function rule represents the table of values? Write the rule in function notation. So before, back when we were looking at linear equations and writing equations from a table or other things, maybe we thought about y equals. But now remember, y is the synonym for f of x. So it just means the same thing. So let's see, what do you have to do this x value to get this y value? Well, multiplying by 3, becomes positive. Multiplying by -3. -5 times -3 is 15. Well, that means the same rule will work for the next one. -3 times -3, well, that's not 17. Let's think about something else. We're going from a negative to a positive, and we're obviously not just multiplying. What we can also look for in the table is a rate of change. So we can find our change in x over change in y. And if this is constant, we know it's going to be a linear pattern, and that's going to help us because we can use y equals mx plus b. Some of you might have already looked at this and saw a pattern already, but sometimes it's going to be harder for you to find it. So let's use our skills we already know about writing linear equations and see if we can build on that. So from here, if I went from 15 to 17, that's adding 2. 17 to 21, that's adding 4. 21 to 23, that's adding 2. And 23 to 25, that's adding 2. So let's see, if I went from -5 to -3, I'd add 2. 2 over 2 is 1. -3 to 1, I'd add 4. 4 over 4 is also 1. Looks like we might have a linear relationship here. 1 to 3, I'd add 2. And 3 to 5, I'd add 2. So notice the change in y over change in x, 2 over 2, 2 over 2, 4 over 4, and 2 over 2. Our slope is 1. So that means we're either just adding or subtracting to get to our output. And maybe you noticed it already, that if you add 20 to each input, you get the corresponding output. Pretty nice. So what does that mean? Well, we know that would mean y equals x plus 20. So that just means f of x equals, x plus 20. So this is the rule written in function notation. Function notation means you have to use f of x. And it matches, each input matches its corresponding output. So explain in words what the function rule represents. It represents each x value. How can we say, should we say added by 20, increased by 20? Ooh, I like how increased by 20 sounds. Increased by 20 produces the corresponding, and because I used x value here, I'm going to use y value. But maybe I didn't use an X value. Maybe instead of the word X value, I used input. If I use the word input here, I'd have to use the word output. Very good. Maybe I didn't use input or output. Maybe I used domain value. Here I'd have to use range value. Cool. Let's keep going. So 2, 3, and 4 are all tables where I'm asked for a function description and a function rule. I'm going to help you out on 4, and then we can go back and you're going to do 2 and 3. Okay, so taking a look here, input, output, so X and Y. And what we're going to look for is first we're going to see, maybe this is a linear relationship. So we want to find change in X and change in Y. So I'm going to use my calculator to make it go faster. -2 to 3, I would need to add 5. -8 to 27, I would need to add 35. So change in Y over change in X, that's 7. Let's see if the next one's 7 as well. 27 to -1. Ooh, I'd have to subtract 28. So 3 to -1, well, I'd have to subtract 4. Okay, so -28 over -4. Well, that's still 7. That looks good. Okay. -1 to -125. I would need to subtract 124. And -1 to -5, I would need to subtract 4. Well, 124 divided by 4 is not 7. So this is not linear. So then we need to start looking for some other patterns. So looking for some other patterns here, I have a negative and I get a negative, a positive, I get a positive, a negative, I get a negative, a positive, I get a negative, I get a negative, and a positive, I get a positive. Well, because of that, maybe I'm just multiplying by a number. But if I was just multiplying by one number, this would be a linear relationship. So I'm not just multiplying by a number. So let's think about what makes a relationship not linear. What type of graphs don't look linear? Well, if you had a square graph, that's going to look like a parabola or a curve. And if you had a cubic graph, that's also going to be a funny curve. So maybe this is going to be a square or a cubic. Well, it's definitely not a square because I wouldn't have any negative outputs. See how all your outputs, your y values, are positive for a parabola, for a square function? So taking a look here, it's a cubic. Taking a look, -2 to the third is -8. 3 to the third is 27. -1 to the third is -1. -5 to the third is -125. So really nice. So let's take a look at this function description. Each input cubed produces or results in or gets you, each input cubed produces the corresponding output. And we have to write our function rule. And remember, we're writing our function rule in function notation. So f of x, your output, is equal to your input cubed. And we don't need any parentheses around this, because remember, if you were going to evaluate, you would put parentheses around your variable. Are all functions linear? Oh, we'll get back to that in a second. So we're going to go back to number 2 and 3. And you're going to pause me, please and thank you, and go through 2 and 3 and start me back up when you finish, and we'll see your awesome work that you did together. Thanks for pausing the video. Okay, let's see how we did. Okay, so if we looked at number 2, you probably noticed that we had a rate of change of 3. Maybe you didn't, but if you go and look at your rate of change, you notice you have a constant change in y over change in x of 3, which can be really helpful here. So to go from 4 to negative 11, you'd subtract 15. And to go from 1 to negative 4, you subtract 5. Negative 15 divided by negative 5 is positive 3. And if you continue looking at the rate of change, negative 11 to 16 would be adding 27. Negative 4 to positive 5 would be adding 9. Again, 27 divided by 9, 3. 16 to negative 23, 6, 7, 8, 9. Negative 39. 5 to negative 8, you would need to subtract 13. 13 goes into 39 3 times. Negative by negative is positive. Rate of change, 3. And then finally, negative 23 to positive 10, I'd have to add 33. And negative 8 to 3, I'd have to add 11, which again is 3. So I know if I thought about a linear function, it's going to be y equals 3x plus my b value. Let's think about this. 1 times 3 is 3. What do you have to do to get to 4? Add 1. Okay. 3 times negative 4 is negative 12. What do you have to do to that to get negative 11? Add 1. 3 times 5 is 15. What do you have to do that to get to 16? Add 1. 3 times negative 8. Well, I think you get the idea. You'd want to check all of them just to make sure. But your function rule is f of x equals 3x plus 1. And for your description, I would say 1 more than each. How do I say? I want to add 1 first. So usually if you have adding and multiplying, you talk about the adding first. So let's see. 1 more than 3 times each input results in the corresponding output. Fabulous. Cool. Okay, so let's take a look at number 3 and we'll look at how you did. So taking a look at number 3, you had 2, 5, 2, 4, and 2. Ooh, let's look at these directions. It says if the relation is not a function, explain why. Notice these x values. If your input is 2, it could go to a 3, a 7, or a 0. If you press the button of 2, you don't know which candy you're going to get. The other thing I like to say, so back in the day when there would be cartoons and there would be this coyote and a roadrunner, and the coyote was always trying to catch the roadrunner. So one time, and unfortunately the coyote wanted to kill the roadrunner. So one time the coyote got this bottle and it had a double X on it, because once the roadrunner ate it, it would poison the roadrunner. So I say double X means poison. Double X means poison. If you have a double X, if X repeats, if your domain repeats, this is not a function. Double X means poison. Okay. So cartoons can teach us a lot. Okay, so here, this is not a function. So we're going to write this. Function description for the input 2, because we want to be as specific as possible. We don't want to just, give the same generic answer all the time. For each input, there is not a unique output. For the input 2, there are multiple output values. You cannot determine the output given the input of 2. Okay, let's continue. Are all functions linear? Explain why or why not. No, they're not. Not all functions are going to be linear. We can have cubics, we can have exponents of 2, only if written in the form y equals mx plus b is a function linear. Okay, I'm going to let you in on a secret. Not all lines are functions. There's one special line that is not a function. All the rest are. So all linear relationships are not functions. And all functions don't have to be linear. Okay. So let's think about what that means. So if you have a function, and as long as the x value doesn't repeat, if you have a relationship, as long as the x value doesn't repeat, your relationship is a function. So graphically, what does it look like if an x value repeats? Let's say I have an x value here. If the x value is the same, what type of line am I making? I'm making a vertical line. So if you're looking at a graph, as long as there's no vertical line segments, or you can't create a vertical line with points in your graph, it's going to be a function. So that's something to remember, that all lines except for vertical lines are functions. So let's take a look. I really enjoy function notation because it makes our lives as mathematicians so much easier. Instead of writing out a whole equation and saying, okay, evaluate when x is -2, evaluate when x is -2/3, evaluate when x is 1/60, multiply it by 2. We can just give the general function f of x and then just tell you what value you're substituting in. So f of x, that's what all of these just mean. It's just giving you an x value to substitute in using your parentheses into the equation. So f of x is equal to, f of -2 is going to be equal to, because we defined what f of x is in the directions, we have 2 minus 3 times -2. Now all you have to do is use your order of operations, multiply first, 2 minus -6, 2 minus -6 is 2 plus 6, and you get 8. So f of -2 is equal to 8. Cool, let's look at the next one. F of -2/3. Well, that means f of -2/3 is 2 minus 3 times -2/3. This is evaluate the function f when x is -2/3. Well, here's the function of x. Substitute in -2/3 for x. 3's cancel out, so we have 2 minus -2. 2 minus -2 is 4. F of -2/3, the function f evaluated when x is -2/3 is 4. Then we can get them into a little more complex, which is really fun. Here we have 2 times the quantity of the function f evaluated when x is 1/6. And it looks so complex, like this is intense math, but it's really pretty simple. You've been evaluating functions for a long time. Now we're just giving it some fancy notation. Elevating it. Okay, so this is twice f of 1/6. So if we go back, this is 2 minus 3 times 1/6. And we're just going to use order of operations again. 2 minus 3/6, which is 1/2. 2 times 1.5. And 2 times 1.5 is 3/2. Or you could write it as 1.5 or 1.5. I prefer improper fractions, most efficient. So what value of x makes f of x equal to 0? What value of x makes f of x equal to 0? So notice f of x is really y. So when does y equal 0? Does that remind you of something? X-intercept, your y. Oh, here you go. My y is 0. X-intercept, your y is 0. Okay, so we're really just looking for our x-intercept here of the graph because all these are graphable. So what value of x makes f of x equal to 0? Well, if f of x equals 0, and we know that f of x is equal to 2 minus 3x, all we have to do is solve for x when y is 0. Okay, I'm going to subtract 2 from both sides and move over here. Negative 2 is equal to negative 3x. I'm going to divide both sides by negative 3 or multiply by negative 1/3, and x is equal to 2/3. So 2/3 would make this function 0. Okay, so what we're going to do is I'm going to give you two functions. I'm going to give you f of x. I'm going to give you g of x. And we're going to evaluate 10, 11, 12, and 13. I'm going to help you out with 11, and then you're going to do 10, 12, and 13, and we'll see how you do. Okay, so there's a couple ways we can do this. We can write it out as one big expression, just like I did up here, or we can, to the side, find g of 3 and find f of 2, and then substitute those values in. So I'm going to find g of 3. Up here, I define g of x as x minus 1. This is the function g evaluated when x is 3. So now we have 3 minus 1. So I know g of 3 is equal to 2. I'm also going to evaluate f of 2. F of 2 is the function f evaluated when x is 2. Here, f of x is x squared. So this is x being squared. So I know that f of 2 is equal to 4. So now that just means that this is 5 g of 3, which is 2, minus f of 2, which is 4. Could you have done this like in 6th grade probably? Order of operations, multiplying comes before subtraction. 5 times 2 is 10. 10 minus 4 is 6. Excellent work, mini mathematicians. Okay, you go ahead and finish 10, 11, 12, and 13. And pause the video and we'll go over it when you're done. Okay, let's see how we did. 4 times the quantity of f of 4. F of 4 is the function f of x evaluated when x is 4. So 4 squared f of 4 is 16. So we have 4 times 16, which gets you 64. Beautiful. Let's take a look at the next one. Here we have f of negative 3 being divided by g of 0.25. So first I'm going to figure out the function f evaluated when x is negative 3. So remember, when we substitute into an equation, we always, or any expression, we always use parentheses around our variable. So f of negative 3 is definitely 9. And then g of a quarter, or 0.25. G of x when x is 0.25. 0.25 minus 1, negative 0.75. So you can leave it as a decimal. I find sometimes dividing with fractions is way more simpler. Negative 3/4. So now back over here, f of negative 3 is 9, positive. G of 0.25 gets you negative 3/4. How do you divide fractions? Well, you multiply by the reciprocal. I can cross cancel here. Negative 3 turns into negative 1. 9 turns into 3. 4 times 3 is 12. Divided by negative 1 is negative 12. Give a nice box or a nice little cloud around your answer so you can find it. Cool. Hopefully you're doing great. And let's go over 13 together. f of 1/2 plus g of 2/5. So f of 1/2, the function f of x when x is 1/2, is going to be 1/2 squared. So that's 1/4. And then g of 2/5. The function g evaluated when x is 2/5. 2/5 minus 1. I'm just going to write 1 as 5/5 just to help my brain out a little bit. 2 minus 5 is -3, so -3/5. So we have f of 1/2, which is 1/4, plus g of 2/5, which is -3/5. To add fractions, you need a common denominator. What's my common denominator between 4 and 5? It's 20, least common denominator. What did you multiply 4 by to get to 20? 5. So what do you multiply 1 by? 5. 5/20 plus negative, you multiplied 5 by 4 to get to 20. So -3 by 4 to get to -12. 5 plus -12 gets you -7 over 20. Is that in simplest form? Yes, because 7 is a prime number. Only factors of 1 in itself. So that's our answer there. Cool, let's get on to our last page. Okay, so these are another way we can show mappings. So mappings can be just with numbers, or we can actually use categories, which is really cool to use qualitative versus quantitative data here to look at our functions. So functions can also describe non-numeric relations. Study each non-numeric relation and its mapping below. Does the relation represent a function? Does each input only have one output? Explain your reasoning. So student's name versus the color of their shirt. So I have Sam, Joe, Luis, and Mia. If I gave you the input, the student's name, would you be able to determine the unique shirt color that that student has on? Yes, you definitely would. So is this relationship a function? Yes. This, get rid of my pens, relation is a function because given a name, you can determine the unique shirt color. There's a lot of ways we could have said this. Yes, this relation is a function because each name corresponds with exactly one color. Sam has on a red shirt, Joe has on a blue shirt, Luis has on a red shirt, Mia has on a green shirt. Each domain value, each input corresponds with exactly one output. We really want to connect to the situation here. So that's why using name and shirt color is really important. So let's take a look at 15. Where a person lives versus the team they root for in college football. Well, if you live in California, can you determine who you're going to root for? If you live in Utah, can you determine who you're going to root for? If you live in Arizona, can you determine who you're going to root for? Is this a function or is this not a function? This is no, not a function. Oops, I guess I should put this relation. This relation, so it's a relationship between where you live and the college football team you're going to cheer for. Go Aztecs. No, this relation is not a function because if you live in California, you could root for the Aztecs or the Bruins. Meaning each input does not have a unique output. The input of California corresponds to two outputs. So our next problem is going to be really important, and I understand these aren't going to be students' names, they're going to be people's names. People's or friends' names. So we'll start. I'll give you Mrs. Barr, recently had a birthday, 4-6. We're going to have inputs and outputs. And let's put a couple more people, maybe that you know. I'll put a couple people that I know. Mr. Barr, one of my most favorite people ever. His birthday is July 7, 5. And my mom, birthday is 4-8. And my sister, her birthday is 10-8. And my brother, his birthday is 2-12. Okay, so let's take a look at our mapping. Oh, and then I have, oops, I didn't spell brother correctly. I have my friend Fred, and his birthday is also 4-8, just like my mom. Okay, so does this mapping represent a function? Is this mapping a function even though Fred and my mom have the same birthday? Or maybe you ask people who are twins. We have a couple cool twins in our class. Would that mapping still be would that mapping a birthday still be a function? Is this relationship a function? Yes. Each person can only have one birthday. Hence, every input has a unique output. Cool. On your homework, it's going to ask you to reverse that and then really think about it. So on your homework, you can use my mapping or yours, but just make sure you have 2 people with the same birthday, if you know what I mean. So taking a look, that concludes our 7.1b lesson. I really appreciate all your hard work. Best of luck on your homework. Do your very best. Be nice to everyone, and I will see you next time. Video bar out.